Have you ever wondered how the sand and stones in your area got to be there? This video will, I hope, explain how these gravel beds came to be formed and what sort of investigations you can carry out in your local gravel pits. This is a map of our part of England, East Anglia. Today the Thames flows out through London into the southern part of the North Sea. But if we go back about 1 million years, then the Thames flowed further north. During the last ice age, called the Pleistocene, there were several periods of ice advance as well as retreat. The periods of ice growth and advance are called glacials, and those of decline and retreat interglacials. The whole period lasted about 2 million years, ending about 10,000 years ago when the ice in Britain melted. This map shows the maximum extent of the ice in Britain during the Ice Age. The arrows show the main direction of ice movement. The ice advances had a dramatic effect on the ancient River Thames. They pushed it further south. The maps show the effect this had. In much of north and central Essex, the remains of the early Thames are found as deposits of sand and gravel. Often, these are covered by younger materials, laid down by a later ice advance. In many parts of Essex, the sand and gravel is extracted from pits like this one, and used in the building and road-making industries. You can see the location of the gravel pit that was visited for the purpose of this video. It's at Weaver's Hill, just north of Chelmsford, near Little Waltham, and the pit is owned by the Mid-Essex Sand and Gravel Company. In order to reach the sand and gravel, the boulder clay overburden must be removed. From the entrance, we get the first view of this site. The water looks inviting, but it's deep and very cold, and it certainly isn't safe for wading. On the far side of the water is the site that's to be investigated. You can see from this distant view a dark-coloured wedge between two lighter layers. Stand well back from the face of the pit and sketch what you can see.
Out there, that clay, I think I have to make sure I get that. And then there's the sand underneath.
That's the top stuff, is it? The clay on top? Yeah. Right.
It's a shame it's fallen down there. It's blocks the layers there. You can't see very well, can you? I think I'll take a photograph of this.
Okay.
Notice that hard hats and sturdy footwear are being worn. This video is accompanied by a resource pack, which will help you to complete your investigations. And it also contains a great deal of background information and extension work. Let's begin to build up a picture by looking closely at one exposed layer in the quarry face. But why are we doing this? Deposits that we can see today were laid down many millions of years ago when things looked very different. By studying them, we can discover many clues, which together will tell us a great deal about what it would have been like here all that time ago. Where do the sands and gravels come from that are being dug out of the ground? Beside the sea? Beside a river? Within a river? Or even in a desert? That's what we're going to try and find out, so let's return to the field.
Right, well the first thing to measure is the thickness of the layer. And we've got to decide that, therefore, which layer we're going to work on. I think if we start here at the top of this gravel layer, this thick gravel layer, you'll see we've got mainly a sandy layer to roughly there. And I think if you could measure that sandy layer with the gravel sandwiched in the middle, that will be okay.
That looks to be about 20 centimetres long now. I'll just check it with a ruler.
And the thickness is recorded on a data sheet, which you will find in the resource pack. Next, we'll measure the range of grain sizes on a grain size comparator. This sample ranges from fine sand to granules. There are also some pebbles, and the largest one is about 40 millimetres long. So record those results. What about the colour? Have a close look and record all you can see. And the rock types? There seem to be a few. And these are recorded. What about the matrix, the stuff holding it all together? We found it to be sandy coloured and consisting of sand. In this area, we found no fossils, so we recorded that. In the resource pack, you will find a flowchart that will be filled in as we go along. You can see that there are various headings, all of which tell us something more about the ancient conditions here. So let's make a start. If you were standing on these pebbles when they arrived here, what would the conditions have been like? Each pebble has its own distinctive shape, brought about by what has happened to it in the past. These shapes range from well-rounded to very angular. And a comparison with this chart will tell you which shape your grains and pebbles are. We classified our pebble as sub-rounded, and this chart tells you that it came from a river. So now we can complete the transport column of the flowchart. If it was a river, how fast was it flowing? The next technique is relevant to most Essex sand and gravels. Pick up the largest pebble that you can find and measure its width, or B-axis. This diagram explains what is meant by that. The B-axis is at right angles to the length. Don't get confused between width and height. The width is the larger of these two measurements. Once we know the measurement of the B-axis, our pebble was 30 millimetres, you can find the river speed or velocity by using the Hailstrom curve. Find the measurement along the bottom axis. Draw a line up to the settling velocity and across to the left-hand axis. Our river was flowing about 100 centimetres a second, so it was fast flowing. Fill that in under the speed of water flow heading. The depth of the water is quite easy to find out. We already know the thickness of the layer. It was 20 centimetres. To find the depth of the water that this was deposited in, just multiply that by 6. 120 centimetres, or 1.2 metres. Quite a shallow river. In many deposits, the pebbles are arranged in a particular way. They lie parallel to one another. Pebbles transported by current action often come to rest overlapping, like roof tiles. The long axis of non-spherical pebbles are often aligned in the direction of current flow. This gives an indication of the direction of the flow responsible. We can easily tell, therefore, the direction from which the water was flowing. This is called imbrication. But you can't always find evidence of it. So what else can we use? Sediments are usually laid down in layers called beds, with the layers parallel to each other, like the slices of bread in a loaf. This is called regular bedding. Cross-bedding is formed where water currents or wind have laid down sediments on sloping surfaces. The sediments are carried along as a surface carpet, tumbling over each other and rolling or avalanching down the front of a moving mass of sediment. Sometimes beds have large particles near the bottom and progressively smaller ones towards the top. This is called graded bedding, and it results from the settling in water of mixtures of large and small particles. We can use cross-bedding to determine the current direction. In order to do this, we apply the principle of dip and strike. The dip is the angle and direction of the maximum inclination of the bedding measured from the horizontal, and the strike is the bearing of a horizontal line drawn on the plane of the bed. We are most interested in the direction of dip, which is measured in the field by a compass and recorded as a bearing in degrees from true north. To find the dip direction, we cut into a cross bed. Here the geologist is carefully cutting down into the cemented layer to expose the plane surface of the crossbed front. Next, he places a board onto the plane and measures the angle and direction of dip with a compass clinometer. This technique is explained more fully in the resource pack. The direction in this case was 157 degrees, which means the current was flowing from the north-northwest. To find out what the climate was like is far more difficult. We need to analyse the remains of plants and pollen to find out what plants were growing. Or look at the sides of the pit to see if features such as ice wedges are present. Together with ice wedges, you may see a lumpy surface such as this, left by regular freezing and melting. In our pit, ice wedges were present, although it's not easy to see it in this shot, so conditions were very cold. So what was it like from our results? You would be standing on the bed of a fast-flowing, shallow river flowing from the north-northwest during a cold climate. This simple story can be given more detail and support by using other techniques from the resource pack. When a sediment is moved around by water currents or by wind, particles of the same size tend to end up in the same place. A sediment which consists of similarly sized grains is said to be well sorted. Where there has been little sifting of transported grains, the sediment consists of a wide range of particle sizes. Such a sediment is poorly sorted. We can calculate a value of sorting by analysing the sizes of pebbles in the sediment. Large particles can be measured individually. You can find out a great deal about sand samples by passing them through stacks of sieves, whose mesh sizes show a regular decrease from top to bottom. After sieving, weigh the amount of sediment retained in each sieve and calculate this as a percentage of the total weight. You can show these results as a histogram or as a cumulative frequency curve. Using the curve, a value of sorting can be found by using the 16th and 84th percent levels and calculating the respective grain sizes in millimetres. The formula for this is shown on the screen now.